for speed control and this is for time control. So 6,000 milliseconds, that will be 6 seconds. I will want a time span of 6 seconds for operation, because it's going to be stretching a good look at distance. And of course, I can also control the speed by putting various numbers here. All right. Of course, I can put any number, but the maximum is 255. All right, 255 for computer science reason, because of the maximum value that that variable can hold. I think it's 256. So I think that is 2 to the power of 10. I'm not sure, something like that. But anyway, 255. But I can vary the speed. All right, so it's going to be moving at a particular speed. All right, so that's the idea. All right, so it's not the programming. All right, so this program is already there and it's going to allow the robot to accelerate. All right, so it's going to allow the robot to accelerate. All right, so that is written and it's going to allow the robot to accelerate. So when the robot is accelerating now, what the activity today is going to be all about, the first activity is for us to see what type of curve we'll be getting. And so if you have your laptop, we don't necessarily have to use graph paper, but our students will use graph paper because, of course, part of their exam, etc., to be able to plot graphs and things. But we're going to use this table. So in Excel, so as we put in the data, we can have a graph being plotted. So we're going to do displacement versus time. All right, so basically even this I will just give you, and of course if you want you can give the students, because you might give them various motions and you may just want them to be observing the shape of the curve. All right, so you have constant velocity, non-constant velocity, or variable velocity, etc. So you might just want them to just look at 10 curves very quickly and just tell you what is variable, what is constant. And so you can just have them have an Excel file as well. So as I put in some data, my point should be plotting. All right, so this is what's going to be. So let me just put in some data just to show you. All right, so this is just demo. So that is what we're going to do now. So it's very relevant stuff. 2.0. All right, so that's the idea. So no fancy software is required. So when they do the experiment, what happens is the graph is plotted for them immediately. And of course you can say, okay, you can then ask them to plot this on actual graph paper. So that's what we're going to do. So we're just going to get a runway. All right, so these robots, all right, the program is already on them for them to be accelerating. So they'll start from rest. And then it will get faster and faster and faster until it stops. So what we want is at specific, well, you can do it, right? So I think some persons were doing it differently, but at specific times you can just record the distance covered, and then we just get a table like this, and then, all right, we should come up with a graph. So we get the graph now. What's going to happen is that we're going to do a little mathematical analysis to get the equation of the curve. All right, using logs. If it's not, all right, if it's not linear, if it's a straight line, then we don't use logs. But if it's curved, then what we will do is to use the log method and get the equation, and then we test. So as a real scientist now, what we'll do is we'll be testing that function in reality. All right. So we have the theory and then we have the practical. All right. What is good? Good. So that is for the first part. So something like this, You can also be talking about changing kinetic energy. So if they get the mass of the robot, you can easily go and move on to kinetic energy, etc. All right? So that's the idea. And there are lots of calculations. Even for mathematics, direct proportion, we can work out what one wheel rotation of the robot will be. And of course, then we can make proportional reasoning calculations. All right, so I will ask them how many rotations to cover 40 centimeters, 25 centimeters, 100 centimeters, etc. All right, so that's what the first part of the activity will be. So wouldn't be too long. So because we'll be putting in here, and then the graph will be plotted in no time. All right, so any questions though? Anybody with any questions? All right.
This is for what level of students?
All right, so basically, so it's basically elementary math, elementary physics. I would say from normally grade 9 up.
The reason why I ask is because you're talking about logs.
Yeah. Logs is 6 cape, yeah. C-sec. Yeah, I know.
You start in math.
And yeah.
And translating non-linear to linear is what
cape, yeah. So that's cape.
That's why I asked.
Okay, because all right, so the reason why I'm doing this one, I think I found this one interesting, but of course, all of those elementary ones where they just use gradient, y2 minus y1 over x2 minus x1, all of those are also there. But it's just picking a specific example.
More than likely you're not going to get a straight line. You're more than likely going to get a curve. What you want to teach them is to find a gradient at a point on a curve.
Yeah, of course.
Instead of, because more than likely you're not going to get a straight line.
Okay, no problem. No problem. So, all right, so we'll get the data and see what we get. So the good thing about it, so all of those different scenarios are programmed. All right, so we have all of those different scenarios that are programmed. So we have straight line example, ones that are programmed. You have curved ones that are programmed. All of those ones are programmed. All right, so that's ideal. Yeah.
In other words, they say you program it to get a straight line.
Yeah, so all of these, yeah, so yeah. Yeah, man. So basically, it's for different scenarios. So the good thing is, you might have one example that you want them to see a straight line, another example you want them to see curves. All right, so even though certain things are not on the C-sec syllabus, but on the CAPE syllabus, the entire thing was just to show its usefulness to the whole process of academics. All right, so that's ideal. Yeah. All right, so you have times when they show you some graphs and they'll ask you which one represents constant velocity and which one represents variable velocity. You can also identify those. They're not going to do the calculations for variable velocity at C-sec, but they'll do that at CAPE. All right, so that's the idea. So, all right, so that is for that. So that is what I want to do now. All right, so right here, so let me just show you one more thing. So all of the codes you'll be given, I will just show you how to download the codes to the robots at different time as well. So you just have that. And of course, you can study the codes, and of course, you can vary or you can request that if needs be. All right, so, all right, I'm just looking for the folder here. Yeah. Yeah, so basically, all right, so all of this you'll get. So for example, some of the codes, so like trapezium motion, as I was telling you, would have programmed several of those already as well. So a car starts from rest, accelerates for a certain time, then it moves at constant speed, then it decelerates. So all of that they do in C-sec. So we have some examples of that program as well. You accelerating for a certain time, or we'll have some that the robot is just moving at a constant speed for a specific time. All right, so those ones, but those ones were kind of easy, so I wanted to do one of the more challenging ones and stuff like that. But of course, we can run through that as well. All right, so what we can do as well is to get the acceleration, which is at C-sec. So we know it's starting from rest. I will wait until it builds up to maximum speed, And once we get that time now, we can use the formula for acceleration for them to calculate the change in acceleration. All right, so that's the ideal. So that's for that. So all of these we given as well. I think I gave them in a zip folder before, but no problem. So I'll just run through, download different stuff, and we'll see how different ones work. All right, so now it's just time for the runway. All right, so we can fire up. So we just need a little runway, and then we'll do this first activity. Yeah, no problem. All right, so it's fairly quick. So I'm going to do a few eggs. All right, so normally, well, some persons, what they do is just to, as soon as it passes a certain mark, they just mark off, but no problem. So the blue button, when you press the blue button, it takes a little while, and then as it moves, you want to complete this table. You want displacement versus time data. Right? So you just need your phone to measure the time and just to mark off the distance. Alright? So that's ideal. So what some persons did, they use the time. So they look at the maximum time that it's running for, and then they say, okay, say it ran for 6 seconds or 8 seconds. They just do 1 second intervals, and they just mark the distance after every second. So anyone works, but this is what it's all about. All right? And there are many different activities in the book, and of course there are many different activities that you will come up with as well. So as you use it and as you do it, you will see many different activities. What one set of teachers did, that some persons, they wanted it on a rough surface, some persons wanted it on a smooth surface, and say the difference. All right? Because I think the wheels were rubber, and it wasn't traveling for a long time, so the difference was, you know, not very noticeable, but yeah.
We look at friction at grade 8.
All right. Yeah, so and there are a lot of different scientific concepts that will come up. All right, and of course you will be focusing on the ones that are at the CSEC level, and then now if it's a CAPE class, you will focus on the ones that are actually at the CAPE level. All right, so that's the concept. So that's the rationale. But of course, knowing the students though, they're going to ask you all sorts of questions that is not on the syllabus. So we can do a practice run. All right. So in terms of the time, how much time? About 6 seconds. All right. So this is the activity part, everybody. All right, so yeah. Well, that was for my purposes. So. Well, I'm going to get this one as well. This one chipped off? Yeah. All right. All right. I guess I can get a footage from you. All right. So who wants to conduct the experiment? All right. So the methodology. So of course we're all physics and computer science, right? Computer science. Well, all science people. Biology as well. Well, we all know about procedure and methodology, so we know the data that we have to collect, displacement and time. So which one are you going with? So you are the experimenters now. Are you going to chop up the graph in time intervals? So let's put it back on the table. Or you want to count up the displacements like 0.2, 0.4 centimeters. Yeah, I'm looking for the Excel file. Where is it? Okay. Which one was it? No, that was velocity. Yeah. Yeah. So yeah. So depending on what you do, we just change the time segments, etc. right? So it's your show. All right, the algorithm is there. The next thing I'm going to do, so we're going to do all of the activities, and then I'll just show you how to download the code. Just attach it, and everything is self-explanatory. So once I show you once, you'll be good to go.
So is it a case where we put in the time that we want it to run and just press the button and that's it?
Well, right now, what happens is that when the robot is going to move, it's going to be just driving, accelerating. So you now have to say, okay, how can I assess this motion? So what you want to do is to record the distance it will cover at regular time intervals. So you can come up with your table. So as I was saying, suppose it covered the span that I programmed it for was say 6 seconds. You can record the distance or the displacement will cover after every second.
This is 2 meters.
That is 2 meters long, but what persons did was they knew the length of the tiles. That's what I saw them do. And so if it even covered 4 tiles and the ruler owner covered 3 tiles, then they couldn't, yeah.
Or just measure the distance.
Or they just measure the distance. Yeah. So they just mark it off with tape, and I think I carried tape. I have tape as well. So if you need the tape, yeah. So this is the experiment that you will do. Oh, this is the tape.
Convert up to 5 meters.
Oh, all right.
5 meters.
Well, no, I let it run out the first time.
So the first time we talk about the that's true about
There. Stop short.
that's it. Yes.
Can be.
The program.
Yeah, definitely the battery. Yeah, so that. We not to change it. Take it out, look. Yeah, take a time to build up the power to the motor.
there's an experiment, I know that, you know, Mr. Finn.
Yeah, I know.
Trying to do a momentum experiment, and I suggest you do it on glass, which is a little smoother.
Smoother, okay.
So you could cut down on that.
Friction.
And sources of error.
Yeah, of course. Yeah, of course.
Probably to get a 2 feet length of perspex.
Yeah, okay. Yeah, I think yeah, man, I can get it. Glass. The glass kind of expensive still. Glass.
That's why I said perspex.
Yeah.
Well, I don't know which one is it. Because
Right. Trust me, I'll have to check it out.
but it's something you just put it in your cost of production.
Yeah, I know. What I know though is like a sheet of glass, a ply sheet, you know, the ply size plastics that they sell. I know that is for $22,000 because I was looking at one.
That's about 8 by 4.
Yeah, for the normal ply sheet. 8 by 4, yeah.
22,000.
Yeah. So I'm thinking that.
Capital.
Yeah.
Capital expenditure.
Yeah, man. So that's the thing. But
just to come a little more closer to the equation that you normally use.
Yeah, that's true. Oh, you press the button? Oh. Oh.
I want to move in a straight line.
Yeah, once it bumps it first and it starts, and it continues to move on that slant. One thing that
feelings are Rudolph aligned this.
One thing that we do to make it move in a straight line is to kind of make the ruler, yeah. And then it, even though sometimes I'll drive over still on, but most times it drives between. But at least it. All right, so I think you have the data for the table. Oh, it needs some misaligned. Can push it in. Can push it in. Which one? Oh, this one. Oh. Yeah, 1 and 2. Cool. So I think this will be on our source of error, right? No problem. Life is never perfect, so good opportunities to get some more sources of error. Alright, so you can type up the table and see what we get, and then
These programs, you can get them to buy straight off market.
Yeah.
but where is it?
The electronic
That's all.
circuitry.
Yeah, man. Yeah, so we just assemble them and the coding is ours and everything. But like this one now, we made modifications to the basic.
Okay, that is solar.
Yeah, but well, a TFT screen, it does displays the formulas that they do in school, all of that stuff. Keeping it to the mantra of hands-on academics.
What is the power source of this one?
The batteries are underneath.
Oh,
Yeah. So that one, the program on that one, I was just letting it do obstacle avoidance, just to show them the application and reflection, echolocation, that kind of thing. Yeah.
So we spoke about the application to IT and ComSci. We spoke about logic gates and stuff. Other than like logic gates and getting students interested in programming, what other aspects of could apply with
Well, I mean,
robotics?
alright, so you mean in terms of application?
Yes.
So, alright, so in terms of, there are plenty applications. There is even the underwater robot now that we have. I think it's the one with some pipes, yeah, down the place there. Drag, air currents, upthrust, Archimedes principle, all of that other stuff as well. So that's the reason for the underwater robots. Yeah, so you have to fit it up and everything. So this, yeah, is from a company, Sea Perch. So you have to cut up the pipes, drill the pipes, everything. So it's a kit. But what we put on it though is it has no program controller. So we have to build a program controller for it. Yeah. Yeah, so that one is for underwater. So again, everything that we do, it ties into the academic sphere. But of course, if you're talking about the after school club, you're talking about competition robotics. So you're talking about mimicking and programming for industrial applications, depending on what the theme of your competition is all about. All right, so this one, they use it a lot in marine exploration and all of that stuff, in terms of search and rescue and all of that kind of stuff, in terms of to map out oil, the pipes under the ocean, lots of applications where that is concerned. So when you build a product, you can think of lots of unique areas you can use it in. But the area that I am just trying to build out though is the academic one, where students have a relevance-based kind of learning approach, where immediately after you teach a concept, whether it's speed, velocity, acceleration, or it's in digital electronics, they can have some real-world connection. So one part of your lesson could be that. For example, so you do your traditional v squared equal u squared plus 2ax. They do all of the examples and thing, and then now you have something pre-programmed, already planned. So for this class, this is what they're going to be doing. They get the data, we perform a real-world calculation, we compare it with the theoretical one. Lots of questions should come up, friction should come up, air resistance should come up. The time that the instruction takes to go to the motors, all of those things should come up. And of course, you explore your source of errors and your precaution, because you always have to consider that in the real world. All right, so that's the idea. So lots of applications. All right, from a computer science perspective now, you can write more sophisticated programs and codes to do more like OOP kind of stuff, object-oriented programming, create more functions to do more things. You can, you know, computer science people, they will go the extra mile and say, okay, this is for this motion, but they're, instead of using the basic approach in programming, they might use more functions and all of that in their code instead of the long brute force. All right, so that's the idea. All right, so everybody has the data now? Oh.
The first one was 5 points.
All right, so tell me the time. Is it what time?
5.30 seconds.
5.30 seconds.
The second one was 6, I'm not sure if it's 6 o'clock.
All right, so in terms of the increments, what did you do? 1 second intervals, like you.
The overall time.
Oh, you got the overall time. Oh, I wanted to chop up the segments so that we could see the acceleration coming up. Because the overall time, we could calculate the average speed with that. Total distance traveled, total time.
Yeah.
So,
Two different distances you use?
Same distance.
Oh, yeah, two different times?
Yeah. But I think that had to do with the starting, the initializing time.
yeah, it builds up before it starts moving, because it's coming from zero motor power, to the actual power that will just cause the motor to start spinning. Yeah, we'll have that. Of course, I look at the first part where you have inertia. So once something not moving, then you don't know, it says no, then it's not moving. So what you did though, that is to calculate the average speed. So we would just want the total distance covered on the total time. I would just say calculate that distance. Yeah. So what you wanted to do was to, as I said, either way, all right, since it's 5 seconds, you can just say, let me just change this to 1, 2, 3, 4, 5. So you just give me the distance after it passes every second. So what they did was that they chopped it up like that, and then after somebody was bending down, and they said time and the mark, and they said time on the mark, and they said time on the mark, and they said time on the mark. And then afterwards they just do the measurement. Oh, okay, that's no problem. That can be corrected. But that information, it has some value. We can calculate the total distance with that. Sorry, the average speed with that. All right, so give them some time to come back. Yeah. So when it starts to move after the first second, you want to know the distance, the second, and it accumulates until it finishes. And then we'll get our graph, and then we can come up with the equation. If it's a straight line, we still can get the equation. So the displacement will be a constant time to time. So we'll find the gradient, etc. So no problem if it's a straight line. Okay, so I think what he said was that you got a time for the entire thing. The entire motion was 5 seconds something. And the only thing, once you get the total distance it took to cover that 5, we can calculate something called the average speed. Yeah, total distance divided by the total time taken. All right, but that does not mean that the robot was actually moving at that speed right throughout the motion. So, yeah. But in terms of a broad concept of knowing, okay, I want to cover this vast distance, all right, and I'm going to be traveling at this speed, you can work out what time it will take you to do that. But it does sometimes in the motion you will be traveling higher. At some point in the motion you might have been traveling slower, etc.
Just like you said for world record, I think they said it was traveling at an average speed of 23 miles per hour throughout
the entire thing.
The top speed was 28.
Yeah. Yeah, because he started from rest, taking my time to build up the maximum speed. Yeah, so when I chop up the motion, you see that at different segments, the speeds were different. Again? Turbo, exactly. When the turbo chip in now, yeah, at maximum speed through the line. Yeah. Yeah, so that data has value. So the time, I think you were saying that the distance, what was the distance you got just now for the entire thing? About say 2 meters? .8. So, all right. So it went 1.8 meters in a time frame of how many seconds?
First one was
5.36. No problem. So at the CSEC level, we can ask them to calculate the average speed. Yeah. So we can ask them to calculate the average speed And then no better way to come to the conclusion whereby the robot was traveling at various speeds before it reached its maximum speed. So of course, so the average speed, right? So total distance over time. So there are so many things that you can do, so many activities that you can do, right? The activities are endless, all right? So we normally have our discussion. Yeah, man, remember it's programmed to, I was programmed it for a set span, because if you, for example, if I make it run through another cycle, it's gonna go all the way 6 meters. 6 meters is 6 of these, so it's gonna go. So we kind of plan for a 2 meter long table. Yeah, so if you notice, I'm fairly accurate, because you say 1.8, so we plan for a 2 meter long table. All right, so, and of course meters and seconds, so that's the average speed throughout the entire motion.
Is it something that we can program on the spot?
Yeah, so that's the thing. So that's the next thing that I wanted to show in terms of, this is the cable, all right? So this is the cable, all right? And of course, when I want to program it now, yeah, I attach it here. All right, so I attach it here, and what I'm going to do, I'm going to download a program. So this one was constant speed. So when it starts, the motors build up real quick, and it runs its cycle at maximum speed, so we can record. So we can do the same thing that we're doing here now, but you will definitely get a straight line, all right? Or they should be getting a straight line, you just draw a line of best fit. So what that happens now is that they will get an equation like distance equal to the speed times time. So when they find the gradient of the graph, that will be the speed. All right, so when they get that equation now, they can still test it. By testing it, what I'm saying is that I will ask them, okay, after 1 second, how far was the robot? They calculate that in their books first, because it's all academics. And then now we allow the robot to run for that 1 second, then we compare. So let me just download one of those programs. So it's easy. So this is where the blue card goes. This goes to the computer. And then it's USB. All right, so you hear that sound. That tells me that I'm connected to the port. So what I'm going to do is I'm going to make it move at a constant speed. And there are a few things that I am going to be doing. All right, so this is going to be the algorithm that I have. As it says, used to study motion, so we just vary the times that it's traveling for and all of that stuff, and vary the speed. Get different type of motion examples, which is countless. All right, very countless. So we can match, we can program any scenario basically. So this is.
Check the time.
All right. All right. 5 meters, no problem. That. All right. So. Good thing. All right. So you said something, put it enough to run 5 meters. There's something that is done in grade 9. Well, it's on the CSEC syllabus called calibration. So one of the things that I was going to do was to calibrate the entire thing. So like how I have now 2 seconds here, I'm going to be moving at full motor power. So I would like to calibrate how far it will go. All right. So no problem. So that it's good to have a chart. So that was one of the things, but I actually wanted, that was a suggestion in the book for the students to do, or the teachers to do with the students. So at every single time that you have, you know exactly the distance it will cover. So you can then start to do direct proportions if things are turning out to be proportional in its behavior, which it should, because the motor speed will be constant at full battery power. All right, so that's another little thing to take into consideration. If the battery is dying, then you know that, all right, your motor is not going to be spinning as fast. All right. All right, so I'm going to download the program. So basically, so when I attach it like this, there are 2 things I want you to do. You then go to tools. All right, sure it's catching everything. You then go to tools. When you go to tools, you're going to go to port. All right, so we have to select the port. So the computer needs to know the port to send the code through. So we have to select the port. And then you'll see communication port, Arduino, is attached to 17. When I do that, I'm good to go now. So it means that the USB port just made establish a connection with your Arduino board. All right, and then now we can hover over here and we can see which one of these to use. All right, so once you hover, yeah. No, it wasn't. That was from before. So this wasn't because of that. So verifying, I can verify the code. This is to upload the code. That is for a new file. We're going to write a new program. This is to open an existing file, and this is to save. All right, so I can verify the code, ensure that there are no errors. So it checks through line by line, and any errors it will tell me. All right, so done compiling. Everything is good, no error. And then up here now it says upload the code. All right, and it says done uploading, right? All right, so it says done uploading. So now I'm ready to go. But before I go, there's one little thing that I need to do. All right, so I detach. All right, so before I go, I need to, I'm going to move these wires from here to over here. All right, so, yeah, because right now, what happens for constant speed, I had to use all of my analog pins, A0 to A5. Over here, based on this board, I have to use specific pins to make it accelerate. All right, so these pulse width modulation pins, what they do, it allows you to send different voltage values to the motors. All right, and of course, as the voltage values increases, the speed increases. But only these pins over here could do that. These ones could not perform pulse width modulation. So that's the thing. So no problem. So the brown wire, so it can just fit one way over here. So I have 6 of these, and there are 6 slots. So it's just a matter of moving from here to here for me to get that constant, all right, constant speed. Go again? Yeah, like jumper plugs per se. All right, so when it's on this side now, it's now equipped for constant motion. So this is a full C6 syllabus now. So it's just going to be, I'm going to just vary the time. It's going to be moving forward. All right, so that's the concept. All right, so that's ideal. So it moved for 2 seconds. I can increase the time. Let me increase it. You said 5 seconds, right? 5 seconds, you said? All right, I'm going to increase the time to 5 seconds. All right, so let's increase the time to 5 seconds. All I have to do is sit here. Let me see. It looks like it moves backward, right? Yeah, it moved backward. Doesn't matter. Doesn't matter. I can turn it around. There's an X code to make it move forward. The same thing. All right, no problem. All right, so if that is the case, I think. Yeah, I know. This one said backward. This one says forward for a time, correct? There was some mix-up. Yeah, forward ever. All right, so, and I'm going to change it. I think it said 5 seconds, but this is proportional. So this was for 4 seconds, so let me change it for 5. All right, the function on this compiler is in milliseconds. So 5,000 milliseconds will give me the 5 seconds. All right, so if I want 1 second, it's 1,000 milliseconds. If I want 2 seconds, 2,000, and so forth. So 5 seconds is enough for this 5 meters? Well, let's see. And those are good questions to just answer by just doing. All right, so, and that's one of the next aspect of learning that is good, just to try a few things. Just try out a few scenarios, you know, and say, learn a few things from experience. Because sometimes we think it all out, and when it happens, I say, really? That was not what I was thinking, you know? So that's not a bad thing to do. So now we are still calculating average speed. Yeah, so we can, yeah, so nothing changes, you know. Nothing changes. So you see the same thing. It's just that now I know that it's because I just programmed it to travel one speed, that's constant velocity or constant constant velocity or constant speed. So my acceleration will be 0. So I know that it wouldn't be accelerating. So I know that's a flat speed. So that would give me an equation, distance equal to speed times time, which I know is linear. All right, and of course is at the c-sec level. So no problem. So the methodology we use to test if it's variable, same methodology we can use to test if it's linear, because we're doing the experiment. We're observing the motion and we're measuring, all right? All right, so I attach the robot here. I have to go to tools again. When I go to tools, I just ensure that it's on the right port. So it's on the right port, so we're good to go there. All right, so it's on the right port. If you want to verify, you can verify the code to see if everything is okay.
You switch over the...
Yeah, it's switched over because now it's on the side for constant acceleration. All right. If I wanted variable acceleration, in electronics we have to do something, pulse width modulation, meaning it's something that these pins can vary the voltage incrementally, but these pins cannot.
So variable is on the right, constant is on the left.
Yeah, and of course that is something that I would just put a nameplate. So on this side for constant and this side for variable. And it's just moving from here to here, and that's it. We have all of the motion scenarios covered. All right? And of course, if I want, this also can make it move constant as well, but I just designed it that way. So we're free. We have a lot of freedoms, but what we are interested in is the moving functionality of the robot. Oh, I didn't download the code yet. No, I didn't download it. I verified it, but I didn't download it. All right, so now it's time to download. All right, done. Yeah, so. Yep. So let's see what's happening in terms of how far it's going. All right. All right. So that's how many seconds? 5 seconds. All right, so let's do. All right, so for this one now, moving at constant speed, we'll just allow them to measure the full distance, record the time, and calculate the speed. But after they calculate the speed though,
These hardware stuff. Going to a store and buying these stuff?
Well, my store is the only store that sells it now in JA.
So in a school scenario, the school would obviously need to have a technician who would be very familiar with all of these hardware.
Yes.
Somebody who has to program it too.
Yeah, you can program it. But one of the things that I do is to just give the videos. So all of the material for learning it is given. But suppose the teacher really can't bother.
Stuff.
Yeah.
Okay.
I will have the books and everything. So because one of the things I took the work out of it for the teacher in terms of the programming, because not everybody wants that, but they might just want to carry out the activities. So
yeah. Also, so those who want to carry out the activities, now you just send them a completed
yeah. So you have the code, and you have the codes, and you have that, and then you also get the training as well. All right. So that's the idea.
Sir, Tech, you're the man who's supposed to be. You laugh. It's IT.
Oh, it's IT, bro. No problem. We'll liaison. What the good thing is that I have a YouTube channel, so I do demonstrate all of these things that I'm doing, so you can really follow and stuff like that. So we're in that age, but nonetheless, we can always do a school visit.
I noticed that when you're downloading the program, you plug this part out.
All right, so really and truly, I auto because of conflict, so voltage conflicts. But you know, it will, if you do it over a long period of time, then it may start affect you. But that's what the manufacturer suggests though. But sometimes I forget, but nothing happens. But it's best practice to plug it out though. All right. Alright, so that's ideal. Because as I say, when I plug in this, the board is powered. And this is also powering the board. So it's really to provide conflict. But there, I think there's a divide, there's a diode. I think there's a diode to block one, but you know, they does still recommend that you do, even though it will not just immediately damage it on the first go. Yeah. Yeah, so for this, when I get the speed, the distance is that speed times the time, and then we can make our predictions. The class activity comes in. So I will ask them, okay, after 0.5 of a second, how far is the robot? They calculate it in the book, they measure, and then, of course, again, they can get the table, they can test to see if it's linear. Yeah, one, and that would be a source of error, because you know that it, yeah.
2.61 meters. What time is it, right? Ready?
Yes.
1, 2, 3, go.
I know it's funny.
Very strange.
Yeah, so those things they take into account. If it was moving dead straight or if it deviated, that will affect your straight line distance covered. Arduino.cc. So yeah, so even these individual boards are sold, but of course, they're sold as DIY. So I mean, people use it to make even 3D printers. You know, once you know the code and you have all the actuators. So trust me, you can put almost 2,000 different sensors on these now. You have the GSM sensor, so you can make a phone call and allow something to happen on your circuit. You can control it by Wi-Fi as well. Okay, you have the Wi-Fi sensors. I have all of the different sensors: humidity, pressure, flame sensor, gas composition sensor. And so the other sensors now is what we also use to bring in the other subject areas, especially the gas composition sensor. There's also a radiation sensor. All right, the alpha, beta, and gamma. But more likely you're not going to be using alpha, beta, gamma because the whole radioactivity thing is dangerous. So, but you can measure background radiation with some of the sensors that you can put on this device. So it's very well supported.
You make like a smoke detector.
Yeah, so gas as well, smoke, all of that stuff. So you kind of just think through your applications that you want it for. Some persons just teach the fundamentals. And of course, you have some person, okay, after doing this, what am I going to be able to do? And stuff like that. So I am putting it in a whole educational package and building out the education industry with this technology. Yeah. And of course, there's the activity manual as well. Yeah.
Is it because the battery is low?
It is a possibility.
Because the time decreasing.
Yeah, trust me. The battery, that will happen with the battery. So you can swap the batteries.
Is there like an indicator apart from the red light that says that the battery is on?
There is when the battery is well low, there's a Bluetooth device that on it that would say the battery is low. But that's when it's really, really low and can barely move. Yeah.
But before that, there's no indication.
No, the only indication is just you saying, okay, all right, it traveled this distance, I want to do it again, it traveled slightly less. And when I do it again, it's slightly less. So, yeah, so energy. So as the energy of the battery decreases, you notice even the kinetic energy decreasing as well.
Is there a charger equipped for the battery? Or
Yeah, man, there is a charger, you know. You know that I accidentally took the chargers out of my bag. I think must have a charger in one of these boxes. Oh. Or in the car. I'd have to check the car to see if I have one. But the chargers are there. So the chargers are there. So that is the ideas. But everybody kind of understand, you know, really what you can do with it, right? Especially when it talks about motion. So I just did motion just to show you the motion idea. But there's kinetic energy momentum as well. All right? And the momentum activities and the works. Yeah.
Would that be significant for you? Momentum, because I am over that side.
What I do is that when I should be trying to put momentum is the whatever is for the arrows and
Fix.
Having as well. Alright, so basically this one is remote control. Alright, this one.
what's that, 6-volt battery? It's a
12 volts. Yeah, 12 volts. 12 volts, yeah. 12 volts, 7 amps, yeah. 20 amp hour. This is per 12 volts, yeah. Yeah, so basically, alright, so this is the ROV rover. So these thrusters allow it to move vertically. So I can spin it in either direction, clockwise, anti-clockwise, and of course I can control the two front ones as well. So one of the reasons for doing this is not only for underwater robotic games and activities, but all of the activities that we do just turns out back to be academic based. All right, we want them to be calculating something. We want them to have a discussion on something. So that's the underwater. These are some of the underwater games. But some of the things that we will do, we will have ruler that allow it to go through certain measurement, certain vertical movement. So once it goes through certain vertical movement, we can have some appreciation of the amount of energy that the motor would have exerted, because we'll be using conservation principles. All right, so if it moves through a certain vertical height, potential energy, so if we get this amount of potential energy, we infer that we would have used up some amount of that chemical energy from the battery, etc. So that kind of thing. All right, and we'll have a discussion around the entire thing as to what other factors are coming into play, all of that stuff. But in terms of like moving objects, we allow them to move objects from place to place underwater. Again, yeah, a tank of water. So again, they will moving through specific distances, so we can calculate the time, we can calculate the speed, the velocity, the acceleration. Right? Next, one of the favorite ones is to upthrust. So you allow it to sink, switch off all motors, and it comes back up. You can ask what is making it come up. Yeah, Archimedes principle, all of that stuff. So they get to see upthrust, and they can get to counter upthrust and the difficulty in moving through the water, all right, or another type of viscous liquid, drag forces, all of that can be discussed. So that is the rationale of it all. And of course, you can then mix academics with a little bit of entertainment. All right, and of course, the Japanese, when they were developing educational robots, they came up with the word edutainment. So you can have a little bit of entertainment and the academics mixing together. And of course, you can have different Yeah, you can have different types of learning sessions depending on the mood or the school year, depending on the coverage of the lesson. All right, so you have done with all of your upthrust formulas, all of your Archimedes principle statements, the law of flotation. You've done it all, work the examples. You may just want to show something to move on to the next topic. All right, if you have it, you can introduce it, and they can, the same calculations they were doing, can do the same calculations here as well. All right, while they're seeing, and of course having a little bit of fun. So you can do fishing, but of course the education content is what we're promoting. All right, the drag forces, the upthrust, the viscosity, Newton's laws, the second law, especially force equal mass times acceleration, liquid pressure, pressure increases with depth, all of that stuff. Archimedes principle, of course, the equations of motion, if you're talking about it just moving in a straight line, you know, what are some of the things affecting the motion? This time it's drag, the fact that it has to force itself through the liquid, and of course, we have motors. All right, so since we have motors, we can talk about electricity and magnetism. We can talk about the motor principle, the motor rule. All right, all of that stuff. So that's the education content. But in terms of the games now, of course, there are various games that you can play. All right, and of course, all of those games, there's some educational activities centered around them. All right, so they're moving a distance, but they're just not moving. All right, so it's a class, so you will have some numbers, we'll know the distance they're moving through, so we'll ask them to perform a quick calculation. All right, we know how difficult it is to move through the liquid, so we'll have some questions centered around drag, air resistance, all of that stuff. Not air resistance, drag forces. If you're moving through a more viscous fluid, we can ask them what they will expect in terms of the movement at full motor power. Would you move faster, would you move slower, and why? All right, so all of this is just experience learning. All right, so that is the entertainment part to it. You can do fishing. Of course, the applications comes in. So after the physics, after the science comes the application. So biology, physics, chemistry, geography. All right, so the application comes in. Again?
What the fishing?
Fishing one. All right, so I think this one, yeah. All right, so you can do underwater fishing, so that's one application, stuff like that. You may tell them that the fish is 2 meters away, you're moving at this speed. You know, at what time will you catch up with the fish? Various things. All right, so that's the idea. So it's all about learning from experience. All right, so in terms of the land robots, we were talking about those already. So we were biased towards the entire physics and mathematics. All right, but there is a coding aspect, the programming aspect. All right, so that they will directly do in computer science class. So as they learn about loops, they'll actually see this being played out in the whole hardware robotics, so that they can learn physical computing. Of course, this one we use for obstacle avoidance, so they'll see the coding, and also in terms of echolocation. So if you turn on the robot and each time you block it, it tries to find a different path. All right, so you can do echolocation. Yeah. Yeah, so these are the two ultrasonic sensors. All right. All right, so these are the two ultrasonic sensors. So yeah, so you can put it on the ground on a book. Yeah, so you will see the principle of reflection. All right. So we study reflection, and we can show them what are some of the applications of using that whole concept in real life. Right, from using it, the reflection from the surfaces to see, and bats use it to navigate all of that stuff. All right, so when you press it, there's a little black button again to press to activate it. On the other side, it says key. Yeah, no, well, you're beside, yeah. Yeah, same ultraviolet sensors.
That's why I can't car without anybody.
Yeah. Put something, brother. Yeah, so many things. All right, so well, this is my kind of vision for the whole tech, to blend it in different places. I was hoping to have the underwater games and all of that stuff, and different places. It could be at the schools, could be at the mall, like science expos. Those places where you can have edutainment, so not learning any deep hardcore science, but it's just popping up. And it's popping up in a way that everybody can understand. Like, for example, how Einstein talked about E equal mc squared is not how it's presented to the general public when he wrote his paper. All right? He wrote some fancy line that I can't remember, no matter how many times I read it, I still can't really say it out of my head. But yeah, but it's just E equal mc squared, and that captures everything that he wanted to say. All right? So that's the idea. So that's the kind of thing that we wanted to achieve with this entire thing as well. So yeah, so the last thing to do is also show you the logic gates part. So ones and zeros, all of that ones and zeros, what can we do with the ones and zeros? All right, so we can apply it to the robotics in general, and we can just apply it here as well. All right, so that's for that. But any questions so far though? Everybody's okay? Any questions? All right, so we can identify logic gates. So we can have an activity. So we know the logic gates, you have the AND gate, the OR gate, the NOT gate, all of the gates, all right? So we can identify them. So we can write them out. I didn't think I put them on the slide still. But we can use these activities for them to identify the gate, and at the same time showing them that the ones and zeros really mean something. I remember doing physics one time, and we're going through the gates and everything, and I would say, sir, big man thing, sir, what is one? What we're going to use this to do? So those questions will become less. All right, while exactly, well, you know, they're seeing it, because sometimes to actually see it on paper and to actually see it in reality, yeah. So for example, like a circuit, like you run the wire and but it don't look like a rectangular box them again, sir. So two different realities, and we trust me, two different realities, really two different realities. So in building sometime a physical circuit, I have to be making it look like a rectangle, a real rectangle like they say in the book, because really and truly it's not their fault, you know, because you're telling me that this is a circuit. Right, with a little bulb. And then now, in real life, I see something like this. I'm gonna say two little wires, right? And then it just goes to, you just go to a terminal like this. And they will be like, sir, this and this are the same? Really and truly, to be honest to them, it don't look the same. It is the same, you know, but it don't look the same. And sometimes that is the thing now, assumption. You know, so we assume and say, because we know this, it must can, you know. Yeah. So that's the thing. So it kind of helps them to map what's happening in their book with the real world. Exactly. So Yeah, man. So it's a lot of things, and even how do you connect it to the battery as well? They're more likely going to see a different device. All right. So we have the gates, and so we can identify the different types of gates. So the gates, 2 inputs. So let's just say write a few of them. Alright, so these are some of the gates, and of course, alright, so I have a little device. I didn't activate all the lights, but I can activate all the lights. Alright, so we can do that together, just to say, for example, I don't know what gate this is, because this is the whole idea, but when I put in 0, 0, I'll look and see what happens on the output. And then I put in 0, 1, look and see what happens. Then I put in 0, 1 in the program upload, look and see what happens. Then put in 1, 1. So after I've looked at the output, I can determine whether it's an AND gate or an OR gate. All right, and there are several other gates, or a NAND gate, etc. So that's what I'm going to be doing. All right, and then that will just conclude, all right, certain things. So we attach. All right, so one light is on. All right, so I have only one light on because this one, yeah. The output is on pin 3. All right, so the output here is on pin 3. So so that is what we're going to be watching for. I can change this, however, so that all of these lights become my output as well. All right, so that would just take a little modification, which we can do right now as well. So let's just do that modification. All right, so let's just sit down and just do that modification. And then now what will be happening is that in computer science and electronics, 1 represents 5 volts and 0 represents 0 volts. Every time you see a 1, it means that there's a voltage. Every time you see a 0, it means that there's no voltage.
That means the first part at the top, that will have been 0, and then I have to have 5, and then I'm seeing another 5, and I'm seeing 50. Is that what you're saying?
Go ahead, say that again.
So you said every time I see 1, it's 5 volts.
Yeah, that's correct.
So this will be 5.
Where? Yeah, that's 5 volts, yeah.
This is 5.
Yeah, that's correct.
But this is 15.
No, man. That's 5 volts on the input terminal A, 5 volts on the input terminal B, and 5 volts on the output.
So it don't add up.
No, it's not adding. C is just the output.
C is the output.
Yeah.
Based on logic gates, both have to be on for it to get the
Light.
Oh.
Yeah.
You see, yeah.
So the name tells you, if both are on, you get R.
But I'm seeing now over here.
That is R. So either one of them must be on for it to get a voltage.
Oh. So you see, I learned something today.
Yeah, no problem.
That is why I'm biologist.
So the name of the
Biologist.
Oh, okay, no problem.
So one virus plus one virus.
Yeah, so it's not adding.
No.
I know it, man.
Alright, so that's input and output. And there are several other gates that are programmed. So really and truly.
And then you have NAND and you have NAR.
NAR is here?
You have NAND exclusive.
Closest thing we learned is, you could relate to this was a stoplight.
Oh, okay.
Years ago, around 25 years ago, the closest to this technology you could relate to was a stoplight. Now we have so much things we can relate to.
Yeah, that's true. All right, so
You know, I'm going to tell you, no, none.
all right, so let's go through the sequence. So on my program on the board, I have 2 inputs. So these are 2 inputs for the teacher. Input 1 and input 2, that's A and B. All right, so based on these 2 inputs, all right, our output will be controlled physically.
So is it a case where we will know which of these boards are the gates for the under and non-under?
Well, I can allow you to know, but what I did, let me show you the folder.
Or we're trying to identify?
You're identifying.
Oh, we're trying to identify.
Yeah.
These that code as people.
Yeah.
Oh, all right.
So these have 1, 2, 3, 4, 5, 6, 7. I have 2 3s, yeah, so it'll be 7. So I have 7. So this.
I didn't get the instruction.
Yeah, no problem. Identifying the gates. So basically, we're going to be getting the inputs, and based on what comes here on the output, we can identify if it's what gate it is. All right, so that's the concept. All right, so what I was saying though, you'd have to just be watching pin 3, because I didn't program the rest of the lights as outputs. But we can. Yeah. So only pin 3, only the red one, this one, you should be looking at. I can allow all of them to be on if you want. So you just have to just modify. Alright, so I'm going to make all of them be on, alright? So this is pin 1, pin 8. Alright, so let us make all of them be on. So all of them, all of the LEDs will be output. Alright, so I'm going to set up all of these. I'm going to have to configure all of these pins. Alright, so I'm going to configure all of these pins. So what I'm doing here, I have 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to have 8 pin modes. So I have to configure all of the pins to be output so that all of them can be activated. So that's what I'm going to do. So I'm just copy and paste in, and then I put in the right pin numbers. Alright, so I'm just going to have 8 of these. Alright, but this you already just get, and you just use. So it's just a matter of having it and using it. You don't necessarily have to code it. But yeah. Yeah. Alright, so the last one now. Alright, so I have 8. So I've connected from pin 1 to pin 8. So that's what you're going to see here. So I'm going to say 1, 2, 3, 4, 5. So is it 1, 2, 3, 4, 5, 6, 7, 8. Alright, so right now only one is activated. So I was just telling it to look at pin 3, but I can just allow all of them to just be the output. So I'm allowing all the lights to be the output. Yeah. Right, so instead of just looking at pin 3. Alright, so this one is like this. So right now this is saying digital write, 5 volts on pin 3, but that is only when the input A is 1 and when the input B is 1. Alright? So because I now want 8 of my light bulbs to light up, I'm going to have 8 digital writes on pins 1, 2, 3, 4, 5, 6, 7, and 8. Alright? So that's why I'm saying that it's... Alright? If you're interested in the programming part as well, it's not too bad to learn, as you know. Oh. Alright, so I need 8 digital writes. That's 1. So I'll now have 2, 3, 4, 5, 6, 7, and 8. Alright, they are all pin 3s, so that has to be from 1 to 8. Alright, so 1, 2, 3, 4, 5, 6, 7, 8. And then, so that's what happens when 1, 1. So you need to copy this. So just activating all the lights instead of one. The low? Alright, because on the down here, when it's not 1, 1, these lights else, these ones should be off. So low means 0 volts. So alright, so now we're ready. Alright, so what I'm going to do, I'm going to start here at 0, 0. And we're going to be watching what happens on the output, and we can identify this gate. So this gate has 2 inputs, input 1 and input 2. Alright, and then now, so the lights are just our output. So the previous code was on it, so that's why you see that one lighting up. So what we can do is check, we can verify, and then we're going to upload to the board. Alright, so let's upload to the board and see what happens. Alright, so all lights are off. So when, so 0, 0. Alright, my output is 0, so I can make a note of that. Yeah. So let this be 1 and then upload again and see what happens. So now 0, 1. I'm now uploading 0, 1. Still nothing on the output. Alright. Change to 0. Let's put this back to 1. 1, 0. Upload. Alright, so 1, 0 is now loaded. Still on. Alright, so when A equal 1 and B equal 1, so let's see what's happening. Alright, so that's ideal. So we can safely say that this is an AND gate. Alright? Go ahead, say that again. Oh, yeah, no, we have to, yeah, you have to, I am doing it from the code. So the wire is attached. So you have to do it from here. So it's something that you could just ask them, you know, of 00, you type in the 00, upload, they tell you what happened. So they will just be filling out the output, and after filling out the output now, they can be able to identify the gate. All right, so that's ideal. All right, this way, I can program any combinational logic. So if I, for example, to say have it fixed, then yeah, it presents a little hardware challenge there. So yeah, so that's the idea. So this is an AND gate. So we can, all right, let's go to another one and see what will happen. All right. So that's an AND gate. All right, let's see if we can identify this one. All right, so let's just watch and see what this one is. So this one, all right, so I've only activated pin 3, all right, in all of them. So let's see if we can identify which gate this is. Yeah. Yeah, you're looking at the red one. Yeah, this red one, yeah. All right, so I'm gonna upload 00 now. So when 2 zeros goes in, all right, so select the board. All right, so they'll be filling out that column, the output column. All right, so let's upload. When 00 goes in, anything happens. All right, when 00 comes up, it's on. All right, next one. Let's see what 01 will be. That is uploaded.
It's off.
It's on.
It's off.
Yeah, it's on. All right. Well, we don't know yet. All right, so let's upload 10. Still on. All right, let's upload 11. All right, so it's a NOR gate. All right, so that's the idea. So basically, we can identify all the gates, and then now we can use the output to also control something. So I could have used the output to switch on a different device. I could have used the output, I could have connected on a relay, and I could be switching on the device, the lights in the lab, etc. All right, through a relay. All right, so that is the idea. And of course, I also have some combinational logic ones as well. So basically, when I put in the inputs, they will know what sequence of inputs will control the output. All right, so that now they can kind of get a sense on to see that these ones and zeros can actually be activating things in the real world. All right, so that's the rationale behind it. And of course, we're physicists, so we promise to keep these things short, but to be direct in terms of, no, I'm sorry. We're scientists. I'm sorry. I'm sorry. No, it's not discrimination. It's just because, you know, I'm a background, but we're computer scientists. We're scientists overall. We're STEM people. All right, STEM, science, everybody, technology, engineering, math. All right, so even the cameraman is STEM with all his equipment. Yeah, so.
So the program,
will have to.
So you will get this, you will have this. You will have this, and
What if you want to take the program board and when you connect this to maybe a sensor or something to actually activate that connection?
yeah, that can be done. Yeah, man, that can be done. So we could have had sensors. In that case, I would have some digital read, and in that case, when the sensor pick up certain things, all of, that can activate. So all of that, if they want all of that, that can just be arranged or just designed and just sent to them. But
So what chip your microcontroller?
this, the Arduino board. All right, so this is the sophistication of the Arduino board now. So you buy an Arduino kit, for example, and then after that, you can design your own robot. All right, you can design anything, flashing lights. All right, so as I said before, we program a lot of stuff for biology, especially when it comes to response and the nervous system, show you how the message moves from that particular point on the body to the brain, what parts of the brain light up, and stuff like that. So we all have all of those activities as well. So the Arduino board, very sophisticated. People do, trust me, almost anything that comes to your mind, because there are thousands of sensors now that comes compatible with the Arduino board. Yeah.
Similar to the Raspberry board, then?
Yeah, similar to Raspberry Pi. Raspberry Pi just is now Raspberry Pi is a computer, so the Raspbian is the operating now.
I was wondering,
Yeah,
concept.
yeah, exactly. The I/O, the same I/O port, but Raspberry is more more complicated. Two is yeah, because it's an OS, it has an operating system. Yeah, so this is cheaper. So to keep robotics affordable, because the Raspberry Pi now is fetching the board alone, it's fetching a decent local price, the Raspberry Pi package. We're looking at just for the board alone over 100 US. That's for just that.
expensive now?
Yeah man, it's no, the kit. Yeah man, it went up. The kit, that is the kit. That is the kit. So not the board alone, but it comes with few little resistors and yeah. So that is the idea. So when it back in the, if you want the, well, you see the thing is the board alone can't help you really. So you need a kit, and that's a kit. So compared to this kit, we can do a lot. So this is like the intro, but this is a lot well supported, and there are lots of different applications. So we explore the application. So after the in-class granular classroom activities, we look at big applications so that students can see, okay, this is where I can go with this, that is where I can go with this, etc. All right, so that's for that. All right, so this is what it is. I have a YouTube channel, Wayne Thompson STEM Club, where all right, all of these little things, you can just go there, and I explain the programming as well. So of course it's not difficult in terms of to do certain things. You just need to know fundamentals. All right, and this is YouTube. All right, so that everybody has kind of access. And so from time to time I just do reviews and a few videos, etc. All right, so that's the concept. So anybody with any questions? But what I wanted to show you though is what's possible, how it's applicable to the education system, and how it's of great value. All right, so I do this. So every time I have my physics class, it's stuff like that. If we're talking about motion, the traditional thing, we do it, and then we do this. But I leave this for last. Sometimes I say, sir, this we shouldn't do first. But I'm saying, no man, we have a syllabus, so I do that because I know that that has to be done, and I want you to have the equations, but now I want you to have that knowledge now to come to the real world and see what happens. You could do it in reverse, up to you. It's for those times when I say, okay, all right, they did this, they did that, they did this, I'm leaving it. All right, how can I leave this topic in an interesting way? All right, have something planned, very hands-on. After you explain what to do, most of the times they'll be the one who take over. The question that comes up will be beneficial to them, very beneficial to them, and sometimes even beneficial to you, because they will be coming up with some interesting issues and problems that you might not be thinking about. All right, so that's the idea. All right, so you have a copy of the book, but this is the latest version of the book, but you have this as well and as part of the packet. But what would be good is this. If I go through the book, quadratic equations and robotics, also use the quadratic equations. So for the math people, for the mathematics, it has a little bit of all of that stuff. Graphs, allow them to do a lot of hands-on graphs and all of that stuff. And of course, the operational amplifier activities, motion activities, kinetic energy, displacement, all right, displacement versus distance activities, and of course some critical thinking activities where they're given some tracks. I would have calculated navigation. So if you have a robotics or a whole STEM thing, where because I created this book with that in mind, where they were doing some local programming as well, they will have to actually put in all of the proper calculations for the rotations of the robot, right, and sequence the code in order to get through this, and of course answer questions on kinetic energy and potential energy, speed, acceleration, etc. Right? So all of those activities are also there in terms of that, and of course the graphs are there, so it's a workbook. And of course bearings for navigation, so just to map the path of a bearing, and then they can probably do certain calculations thereafter, but they can physically see it. So it applies to bearings as well. So that is a true embodiment. So we talk about kinetic and potential energy going up a ramp, so we explore that as well. And of course Newton's second law, where we have weights. So we put different weights, attach different weights, and see how it accelerates with different weights. And so we can come up with some kind of practical understanding or an intuitive understanding of what really is going on with the formula F equal ma from a visual perspective. All right, so that's ideal. So that's what it's all about. And of course, acceleration and momentum is covered from a practical standpoint as well. And of course, direct proportions, etc. So for direct proportion, we do something that is called the calibration, as I was telling you. So we need to find, when we find out what one wheel rotation for the robot is, so for what time should the robot be moving to cover one wheel rotation, we use that data now, right, to answer other problems. So for it to go through 10 wheel rotations, they have to work that out. For it to go through 15 wheel rotations, then make a right turn, then go that, they have to work out all of that. So calculated navigation. So it's really scientific work. When they run up into problems, they will be able to discuss their sources of error, etc. All right, so that's ideal. So this is the latest version of the book. All right, so the chapters, distance, display. Yeah, so you have that book. So the first book was, everything in the first book is here. It's just that now book company took it over, so they put it in colored, and I just put some pictures in it. But the content you have already. All right, so that's ideal. So that is what it is. So this is the academic version of the thing, and of course you have your robotics club where that is geared towards programming to solve certain real-world challenges as well. But to tie, once you tie in this, it finds its place in the school system rather easily once it's this academic. There are other aspects of this that we explore in this kit. Though in this kit, of course, separate from the logic gates, you have voltage, current, and resistance that are explored. The applications of just basic electricity, that is explored. Of course, sensors, that is explored. And also in the kit come motors. So all of the motor concepts, you put a small voltage, you observe how fast it's spinning, put a higher voltage, notice it's spinning faster. So you can have all of those correlation between voltage and the speed of rotation, or between voltage and the force you get from Fleming's left-hand rule, to go deeper into the whole academic thing. So that is the rationale. So the rationale of the whole STEM is an interdisciplinary approach. So even if you're learning something in robotics, sometimes we even get that idea from biology. All right? So that kind of thing. We perform comparisons with the nervous system, the robot, electronic circulatory system, and the nervous system of the body. What are the similarities? What are the differences? What carries the message to the robot motors? What carries the message to the brain? Are there similarities? Yes. When these impulses in the body are moving, what are those impulses? Still electricity, right? Still have some form of electrical signals or stuff, right? So lots of similarities. So the next thing was to kind of bring it all together. Students have a holistic way of learning, right? So they can be innovators, better thinkers, appreciate science more, you know? So that's the whole thing. Appreciation. They will pay attention to it, or it might just be that they're at a place where, okay, now I see what I can really do with these formulas, or now I see what I can really do with logic gates. I can see it because we did it in class, all right? Stuff like that. So things becomes more relevant. So we're teaching for them to understand the classroom in the real world, all right? So thank you for having me. Any questions? You have my YouTube channel and also phone number as well, and of course can always available at a strategic time for a presentation. All right, so that's the idea, but that is the vision. The vision is for hands-on learning, relevance-based learning, and for them to be timed up. So when we talk about science, we can seamlessly transition between the three sciences in terms of what is similar and how this relates to the other sciences, etc. That's the concept. All right. All right, so if there are no further questions, it's that time of day.
I think that's it.
Yeah.